Additionally, if this structure is subjected to lateral forces like winds, floods, etc., footings will help your building avoid sliding as a result of frictional resistance between the footing and the soil. Now the second design aspect, the thickness of the footing. The footing has to withstand pressure applied by the soil as well. If the footing's thickness is inadequate, the footing on either side of the column will bend due to the soil applying uplift pressure on it. This effect is called applied bending moment. You can see this effect in this FEA result here. To prevent this result, the thickness of the plate is increased. There you go. We have designed a stronger and safer footing for our building. This type of pad or isolated footing is employed to support lightweight houses that rest on soil with medium strength. This design can be further optimized economically. If you observe the pressure applied from the soil on this area, it is uniform. However, applied bending moment increases as we come to the center zone of the footing. Thus, the need for footing thickness in the center is greater than at the edges. Therefore, a trapezoidal footing shape has been adopted in modern structures for isolated footings. However, a pad-type footing is used in other more complex types of footings. Suppose your building's columns stand exactly on the edge of the property line. Obviously, your neighbors won't allow you to take up extra space simply to extend the footing. In such a case, the column is placed on the edge of the footing, causing all loading transfer on the soil to become unbalanced or eccentric. This footing can carry a considerable amount of load on the structure. However, if the load increases beyond a certain limit, the structure may fail. The trick to solving this problem is transferring the excess loading into another adjacent footing with good strength. This transfer is accomplished by placing a connecting beam in between, which acts as a strap. One of the columns in this strap footing will generally have an eccentric footing. Moreover, in some cases, when the columns are too close to each other, engineers purposely combine the footing. In most modern heavy buildings, the structure's columns are provided with combined footing as a whole. A single reinforced concrete slab is made for each and every column. These footings are called raft or mat types, and they spread the load evenly imposed by a number of columns or walls on the soil. This type of footing is adopted to avoid deep foundations, which would otherwise go around 60 to 200 feet deep. In an area with expansive soil, the raft foundation is a boon that lessens the chances of differential settlement. The Burj Khalifa uses a combination of raft foundation and piles, which forms a combination of shallow and deep foundation.